fix the sound live and so we can all right. Good morning, everyone. Welcome to week 8. Few pieces of news. First, I hope everyone's staying safe. It looks like we're in lockdown for a few more weeks. I guess the upside for you is you've got lots of uni work to do, so you probably couldn't be going anywhere much in the next couple of weeks. Fingers crossed we're out of lockdown by the time exams are finished and you actually have the opportunity to do a few things. COMP1511, like everything else at UNSW, is online. Is online for the rest of the term. So we'll know more about what's happening next term in a few weeks' time. I expect the uni will make an announcement a couple of weeks before next term about what we're doing. All right. Exams. Oh, my audio's a bit loud. Let me just tweak my audio down a bit. Exams. The provisional exam time has been confirmed, so you've got your exam time. We'll be given, in fact, I think we've just received a list of students with clashing exams and things like this, and we're sorting out what we do with this. We also get a list of students who have special exam conditions, and we'll sort out that. We'll get in contact with you before at least a week out from the exam and tell you what's happening if there's something special about your exam arrangements. So please don't contact us now. We don't know the answers to some of these questions now. If we haven't contacted you by a week from the exam, by all means, email the class account, or if it's a more general question, post in the course forum. But we'll sort out exams, and there'll be lots given to you about the information about the exam, generally for all students in the week 10 lectures. Today's lecture is going to focus on linked list, which is the topic of this week's lab exercises. And it's at the heart of the assignment. The assignment 2 is just out. There's a couple of things that are still being finished off. Nothing that matters as far as you reading about it. What are we doing for assignment 2? This week in the tutors, the tutors will try and help you with the background, sort of the context of assignment 2, what it involves, give you some information to help you read it. You might start reading it before your tute. I'd recommend trying to start reading the assignment 2 before the tute, and then if there are things you're stuck on understanding what you have to do, ask your tutor. Next week's tute will be more, how you're going, what problems have you hit on the assignment. So by next week's tute, you should have made some progress at coding for the assignment and have questions maybe for your tutor about things that are causing you problems with coding. When will we give you more information about assignment 2 other than that? So Zoe, who actually basically did most of the tutor, did most of the development for assignment 2, is teaming up with Tom in a live stream 5 o'clock tomorrow.
5 o'clock on Wednesday.
Yeah, tomorrow's Wednesday. You're good. Wednesday, tomorrow, 5 o'clock, 5 to 6. The link will be on the lectures page on the class homepage. I expect Tom will circulate an announcement anyway. And we also have Alvin with us today listening to lecture, because Tom's got to go off and finish up sorting out what's happening with assignment 1. Assignment 1 will be in the tutor's hands very shortly, by tomorrow, and they'll give you they'll do some style marking, tell you how well your code reads, try to give you some feedback about what your code's like for a human. Tom's already set up the run auto marking, which has put your code through automated tests to see how correct your code is. I give you a code an input, and does it produce a correct output. So you should have your assignment 1 marks pretty soon. We'll see what we can do there. Please be patient with your tutors, by the way. All your tutors are students themselves, and they've got their own courses. And just like 1511 is getting super busy, every other course is getting super busy. So your tutors are not only trying to help you, but they're trying to cope with their own courses as well.
We'd expect that for the majority of students, we'll have your marks back by around the middle of week 9. That's sort of our goal. There'll be some students, especially those with special consideration, those sorts of things, who might get it back a bit later, but that's the goal that we're aiming for. And if you don't get it back by the end of week 9, feel free to just send your tutor a little message saying, do you know what's going on? We're sure that, things sometimes occasionally get missed, or occasionally one assignment will go astray, and it's very easy for us to fix up very quickly. But just if by the end of week 9 you haven't gotten your marks back, that would be a good time to let us know. But otherwise, we should try and get everyone's marks back by the middle of week 9 or so.
I would say we try to write assignments with no surprises. So when you hand in your assignment, you should have a pretty good idea what mark you're going to get. So, but you'll have your actual mark hopefully within a week or so. All right, Tom and Alvin, any other things of general interest we should be announcing to the class?
Nope, you've gone through my list, I think.
Okay, we're good to go then on today's content. Well, I think we'll be saying goodbye to Tom, who's heading off to sort out assignments 1 and 2. But Alvin will be staying with me and trying to keep me on the straight and narrow, and also checking out the chat and passing on anything from the chat. I try to keep one eye on the chat, but it's really hard to. So Alvin, we pointing out if I miss anything. On screen, I've been scribbling down a little bit of code on screen. All right, so this is your standard main. There's nothing exciting there, but this 4 lines of code will be our intense focus for the next week or two. Yes, the next 2 weeks, and it will be the topic of exam questions, tutorial questions, weekly tests, and assignment 2, all revolving around just those little 4 lines of code there. All right, it's a struct definition. Oh, yeah, it just occurs to me, it doesn't matter. I was just looking at it, which is the best order to put those fields in. Doesn't matter which order we put the fields in. Not as far as we know. There are subtle issues with which we'll talk about in another course about which order the fields go. So the order doesn't matter. It's what the fields are. One is just an int field. That's a bit dull. The other one though is the really exciting one. We have this sort of struct, a struct node, and inside it contains a pointer which can point to another struct node. It's a reference. It's self-referential. So if we can create multiple struct nodes and have them point to each other. Now we're only going to explore this simple type of struct with one pointer to, and we're going to arrange them in particular ways. But this is actually your first step, if you're in a computing degree, into an amazing world where we construct complex dynamic data structures using pointers to link objects together in amazing ways that create all sorts of possibilities. COMP1511 is the core computing course. It's the classic computing course that every computing degree has. Is that there's a course like COMP1521 which really takes you off into this in full. I mention that in particular because I often get students asking me, which comp course should I do next after COMP1511? Now, I can't give you absolutely blanket advice. Particular programs have particular setups, and if you're not a computing person, then you'll have different arrangements as well. But if you're in a vanilla computing degree, a standard computing degree, and for most students, the key course to do next is COMP2521. Where you dive off into this world. But let's take our first steps rather than think about where we're going. All right, so I've got these data structures. What's the possibility? Let me flip to a lecture slide that shows you the possibilities that this structure creates. What we're going to do is use these pointers to link these structs into a list. So each one of these structs has a pointer which will point to another one of these structs. It'll have a pointer that will point to another one of these structs. It'll have another pointer that points to another struct. There are a couple of things, 3 things I think I have to mention. What about the last struct in the list? It will have a special value. It won't point to any other struct. It will have this field here in it will be null in the last struct in the list. So that's one key thing we're going to do. When we link these structs together, we're going to use a null value, a null pointer in the last struct in the list to say you're at the end of the list. And that there's a bit of deja vu there, isn't there? This is like the 0 in an array to say you're at the end of a string. So using a special value in an array to say you're at the end. Our special value here is a pointer that's is the null pointer. What else do we have to do? We're going to need to keep somewhere separately, not in a struct, somewhere separately, in a separate variable, a pointer to the very first node. So we're going to have some way to get to the start. Once we get to the start, we can get to the next one in the list. And if you can get to it, you can get to the next one on the list. And if you can get to it, you can get to the next one, all the way to the last. But you've got to have a special pointer to get you to the first one of these structs here. One more thing. This is sort of someone in the chat's probably asking already. He's saying, but what about this pointer goes backwards here? We're not going to do that. So we're going to keep our lists linear. We're not going to let our lists get circular and loop back on each themselves. So our lists are just going to go struct, 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 end without looping back on themselves. This is an exciting enough and a complex enough sort of working with this is complex enough without worrying about loops. And by the way, so if some of you have done a lot of maths, you're saying, oh, I can implement graphs with this. I can implement, yes, you can implement all sorts of things with pointers like this, and that's how so much of the world's computing is done. But let's understand all the ramifications of this just 4 lines of code here. Well, let's understand some of the ramifications of what we can do with just this little piece of code here. Okay. Ooh, I don't know what's happened there. Oh, all right. Yeah, let's do a bit of motivation before we go further. So here I'm just assuming there's an integer here. That's our workload, our payload. It's some piece of information that we want to store in the list. You're saying just an integer? Yeah, it could be anything. So in real coding, it might be something more like this, where you're storing a pile of information or large arrays. It could be anything that's stored there. But we want to understand how to manipulate these lists. And for these purposes, for the code we've got to write, the program we've got to write, the algorithms we've got to figure out, it doesn't matter what we're storing in our list. That doesn't affect our code. It's manipulating the pointers that matters. So rather than just have all this complicated stuff here, we'll often just say, oh look, there's an integer there, and that's just to keep things as simple as possible. But real code would typically have other stuff there, probably maybe complicated stuff there. Okay. Oh, all right. So let's that's where I want to go now. But let's look at coding that up. Let's look at creating a function to create one of these structs, and then we're going to call it multiple times to create multiple of these. So what's my problem? I want to create something that looks like this. I've got to create 4 different struct nodes here and set up their next pointers to chain them together. How do I do that? I'm going to write a function. And I'm going to call that function createNode. And down here, I'm going to call it all right. So, how do I do this? I've got to supply 2 things to create a node. I've got to supply what the value of the next field will be. Call that in. You could call that next. There's no problem with having a variable the same name as a struct field, and a lot of code will do that. But just to make things clear, I'll keep those names different. What's this going to return? it's going to return a pointer to a new struct node it's created. Alright, so I'll give it the value for the next field, a value for the data field, and it's going to return to me a newly created struct node with that value put in the next field, that value put in the data field. And let's create one that's got, I don't know, 42 in its data field, and I'll put null in its next field. Alright. Let me grab this. How do we create a struct node? malloc is our friend. This gives us a piece of memory, and that's under our control. So malloc, what's its argument? Number of bytes we want. Now, I've said a number of times, but it's a word. New programmers. It's very hard to repeat. You need to hear this multiple times. You don't go here and figure struct node. I think that's 8 bytes, and that's 4 bytes. So I think 8 plus 4, that's 12 bytes. That may or may not be correct. What we always do with malloc is we use size of. Size of is the C operator that says how many bytes does this need. And I say to C, how many bytes does a struct node need? The classic mistake, by the way, another classic mistake is to say that's how many does a pointer to one of those need. No, we want to know how many bytes. So students often put a stray asterisk in there to say how many does a pointer to a struct node need, which is very different to this. This is how much do you need for a whole struct node. Have I got my brackets balanced? Oh, it looks like it. Alright. So that's size of's weird syntax, which you'll get used to. Size of brackets type close brackets. What do we put this in? New node? I think we'll call it new node. Equals. A new node is a struct node star. Lovely. Now, I can finish this off. We're going to return the new node. Yep. And we want to initialize its field as well. So new node, the pointer will be in. New node. It's quite nice. It's a 6-line function. You'll remember with assignment 1, we're talking about. I think I was talking with Tom about the assignment. I was saying, oh, I like functions that are less than a page, 10 lines. You get functions down to 10, 20 lines. That's good. But here we've got a 6-line function. It's always nice when you're writing small functions. It's not always easy to do that, or even and often possible to do that. But in this case, we can compose nicely down to this 6-line function. Let's try. I think that in total, unless I've stuffed up, is a correct C program. So I'll try saving it.
You probably need to lose the underscore over at struct node.
So Alvin says I've made a mistake in my code. I put it in the wrong file. I put it in Battle Royale, which is our example to come. Let me. Actually, no, it's actually not a bad thing. We'll leave it in Battle Royale. That's actually... Alright, so Alvin, can you spot it? An error. Alvin can spot it. I actually can't spot it myself, so I'm actually going to go on ahead and compile. Probably there's people in the chat. Oh, I spelled linked list with a capital L. I don't like that. But Oh, all right. So there's this. There's a stupid typo there, and a stupid typo there.
And I believe Juan pointed out that your order of parameters may not be correct when you use it in line 11.
Incompatible conversion. What the hell does that mean? Passing argument to parameter n here. Warning. Incompatible integer to pointer conversion passing into parameter of type struct node star. Well, what it means is what Alvin has just passed in from the chat. Thank you, whatever it was in the chat. It means I got my parameter order wrong. Thinking, why can't the C compiler say you've swapped parameters 1 and 2 there? You try and write a C compiler and you see how easy it is to give that sort of message. So, yeah. Which order do I like? I don't mind. Alright. The order. Actually, I'll swap them here. I think it's probably nicer to do it that way. That's another thing you can get into arguments with programs. It's not as good as what editor you like, but arguing, you can get into long and pointless arguments with programmers about what order is the best order to declare the arguments to a function. And you can come up with all sorts of reasons that don't really matter. But it does matter if you use the same order everywhere. You have to be consistent, of course. So hopefully I'm consistent now. Yeah, that looks good. Alright, let me compile again. Getting close. Implicitly declaring library function. Oh wait. You've forgotten the hash include stdlib.h. Yes I have. Alright. Let's run this program. Oh, alright, we'll even put it where it's supposed to go. Oh, that's right. Yeah. Alright. That's a lot of work for a program that outputs nothing, but at least we don't get a runtime error. So there are some possible errors that are not occurring. We haven't got a lot of confidence the program does what we want, but we've created a node and then that program returns without doing anything. Well, we need a function that prints a whole list. And what's it going to be? We'll call it print list. And it's going to take a pointer to the first thing in the list. It's going to print out the whole list. We don't have to do all of this yet. So its job is printing lists, so it doesn't need to return anything, so it can be type void, and it just needs one argument, a pointer to the first thing in the list. This is going to need a bit of work, so we'll come back to it. Okay, we'll put it here. That's probably a good spot for it. Yeah, I can't quite see how to print a whole list, but let's get started. Let's print the first thing in the list. We'll just print the pointer. Sorry, the data field. Our little payload of information that we've put in this element of our list. I'm hoping that will print 42 if I've got everything right. Come on, no syntax errors, no syntax errors. Oh, and that's it. There we go. Oh, I have to call my function. Oh, I have to put the... Alright, so we need to point it to the start of the list. Let's point it to the first node in the list. You can call it start, but everyone calls it head, so we'll call it head. Not having a good day. I mustn't have saved that. Save it. Compile. Alright. We've created a list of one thing. Let me go back to my slide. So I've created a list which has just got one thing in it. This is null, and that's 42. So we've created a one element list. How do we create a 4 element list? Let me show you that then. I've got a diagram for this. Oh, that's what we're going to do. Yeah. Oh, so that's what we've done. Oh, that's got a 5 in it. All right. Let's fix my code to be consistent with that. We'll put a 5 there. So that code creates this. We've got the head pointing to one element. The next field in that element is null, and the data field is 5. So that's what we've got done as a diagram. This diagram matches this code. Notice our call to create node supplying the two fields. Alright, what do we want next? I think we have a diagram of, oh, how do we get this situation? How do we create a 2-element list? We can do that. Let me show you that. And it's not hard. We just need one more call to create node. Alright, this list element, we're going to tuck a 4 in. And its next field has to be a pointer to the list element we've just created, the struct node we've just created. Currently head points to that, so we'll pass head to be the next field there, and then we'll set head to be that new node. And we do all of that in just one line of code. We'll compile that, run that. So we're printing out the 4. How do we print out the 5? Yeah. I'll show you how we print out the 5. What we need here is something more general, but we're given the head of the list. How do we print out, if we've got n is pointing here to the first thing in the list, how do we print out this 5? This is n arrow data, the data field of the struct n points to. This is n arrow next, the next field of the struct that n points to. So this is n arrow next arrow data. Let's try that out. I encourage you to try out little programs like this and see what they do. It's no good trying to figure out things about basic things about pointers in the full context of assignment 2. You need to figure them out in small programs. Lab exercises, that's why we've got lab exercises this week to try and get you to practice these ideas in little contexts where you can focus on the basics. But you can write your own little programs as well. Alright, so I think that will print out 4 and then 5. I think if I save it, I'll print out 4 then 5. Oh, that's a little sad. I've got an error. Didn't actually notice that error either. Alright, let's look at accessing a field via null pointer. So yeah, you can't ask in C, say, what does this null pointer to? If I say in data and in is null, that's an error. If I say in next data and in next is a null pointer, that's an error. And that's what DCC says here in that horrible red. It's saying you're trying to say in next data, but in next is null. Why is that? Well, the problem is not this code. This code does what it's sort of supposed to. The problem is back up here. When I created this list node, what do I want? I wanted the data field to be 4. Yep. But I wanted the next field to refer to the first list node we created, the one containing 5. And I didn't do that right. Accidentally. Sorry. How can I make that happen? I can put head in here. And that should fix my problem. Alright, I'm going to roll here. Let's have a look at my next diagram. Oh, look at that. I want a 3 there. Yeah, I think I can do that. I think I can do that just fine. Let's run that. Oh, all right. If the list has 3 things, and I think I'm going to need 3 printfs to print it out. Yeah, this print list thing is looking pretty broken, isn't it? All right. So just so you know, this lines 21 to 23. They're not a good way to code this, but they're what I'm doing for now. Now, let me take a breath and give you some life advice. Something that will make your life, as a coder, happier. You're less likely to be awake at 4 AM trying to fix a bug if you take this advice. Alright, it's analogous to another piece of advice. I gave you a piece of advice about square brackets. Every time you use square brackets to index an array, I said ask yourself how you know the value between the square brackets, the array index you're using, is valid for that array. How you know it's in the range 0 to n-1 if the array is of size n. How do I know this value? If you can't prove that to yourself looking at your code, you probably need to change your code. You might need to add an if statement, a while, you might need to do something. Sometimes you can prove it to yourself because you look at the specification you're given. It might be a test question that says you can assume n will be in this range, so you can prove it to yourself that way. Sometimes you can look back at what's in the preceding code. It's in a while loop that executes so that I is in the appropriate range. But some way or other, you have to ask yourself, how do I know this is valid? Now, linking structs together with pointers, we're suddenly free of this fixed size. We don't need to say beforehand how big this list is going to be. It's one of the reasons we love this data structure is we don't have to decide beforehand how many things we're going to link together with pointers. We can just add an arbitrary number. So we don't have that sort of constraint. But the question we've always got to ask ourselves is, every time we dereference a pointer, there are two ways to dereference a pointer. One is asterisk, but in this stuff we're going to be using arrow to dereference a pointer or follow a pointer, because we've got pointers to struct, and we're almost always going to want to say, here's a pointer, tell me the data, tell me a field in the struct that this pointer points to. Every time you use an arrow, ask yourself how you know the pointer is not null. Now if I look at this code, there's no way to know that. I don't know. I want to know that n's not null, the next field of the struct that n points to is not null, the next field of the struct that the next field of the struct that n points to is not null. I want to know that they're all not null. So this code 21 to 23 just looks broken. I guess I could put a comment here. So you could put a comment here. That would be one solution, saying always give me a list of. So you can insist, you can pass the burden back to the caller of your function, saying I only work if you give me a list of 3+ nodes. It's not very satisfactory. It would be much better to write a function that could print out a list of any number of nodes, and we'll get to that shortly. Alright, we've created this. So we've called malloc 3 times. Malloc has given us this chunk of memory, this chunk of memory, and this chunk of memory. Each of those chunks is maybe 12 bytes. We don't know, we don't need to know. And it holds 2 things. A data field, which is our little payload. In real code, this could be complicated and large. It could be 1,000 bytes. It could be 10 different things. But for simplicity, we're just assuming in this code, it's just a number. And a pointer, and that's the exciting thing. The next field in the last struct contains a special value null. Otherwise, the next field takes us to the struct that's next in the list. We've got a special pointer somewhere at the start of the list. The special pointer in this code is stored in this variable here called head. And here we create a 1-element list, then head points at a 2-element list, and then head points at a 3-element list. And you'll notice that 5 is the first thing in the list, but then it's the second thing in the list after this operation, and then it's the third thing in the list. So we're putting things on the front of the list. It's easier to put things on the front of a list linked together like that if you think about it. If I want to add something, I could change this field to point to another node, couldn't I? But that's a bit trickier. The way I'm doing it's actually simpler. You will get to do both. Oh, you will so get to do both, but not just yet. All right, let's put my last thing in the list. Or do we have a slide for it? Oh, come on. All right, I want to put one more thing in the list. I don't have a slide for it, but let's actually no. All right, let's stop there. That's a 3-element list enough. All right, so let's correct this unsatisfactory code. Let's look at other ways of doing this. Let's get rid of this restriction. We want to make this print list work with any amount of code. How do we do that? Let's get another variable. I'll call it, I don't know, P. There are a few ways to write this code. Let's make it point to the first thing in the list. do we make P point to the next thing in the list? P equals P next. So I could rewrite this code sort of like this, couldn't I? And that does the same job, if I haven't stuffed up. Let's ask DCC. Have I got it correct? DCC says, yeah, that's okay, Andrew. That looks like correct C. And it does the same job. Prints out the 3 elements of the list. Saying you've just made that more complicated. Yes and no. We notice lines 23, 24 are the same as 25, 26, and 27, 28. So I'm thinking loop. This is our stepping for moving down a list. So that's what's the equivalent of an array. If we're indexing an array, this is the same as I equals I plus 1. You've got move your index to the next thing in the array. It's more complicated with a linked list, but if P is pointing here and I want to make P point there, that value's here in the next field. So I say P equals P next, and then that makes P point there. If I execute that again, P will point there. If I exit again, P will become null. So let's just make this execute forever. Now that's a broken program. I can run it though. That loop never stops. So yeah, it's not a good program, but we can actually run it and see what happens. Pretty sure we'll get an error. Yeah, what's happened here? Line 24, accessing. I've run this stupid code to show you the error because when we're working with this code, this is an error we're going to get. We're just going to get this. Accessing a field by a null pointer. I've tried to use a null pointer. Alright, this line's pretty simple. There's an arrow there, so P must be null. I've looked down here, yep, P's null. So that's why the error has occurred. This is saying, look, you've stopped here. Alright. Let me introduce you to part 2 of our loop that executes down a list. We know to stop when we get to a null pointer. So we want to stop when we get to this field here. So if we do P is the next field of what P points at, and P is null, we're done. P, we've printed out the last thing in the list. What could we say here? Let's put a little comment. What do you say there? Something like that, maybe. I don't know. But this, 2 comments for you. But this is the crucial thing here. Our stopping condition. Let's try this out. Make sure I'm telling the truth. It does actually print the thing in the list. Then we'll simplify it and look at it. Let's save my file. Yeah, sorry. Alright, so there we've got code to print any size list. Does it matter if n is null when this function is called? We call with n null, what happens? Then p is null, and then the loop exits. So remember I said it makes your life happier if you always know when you use a pointer that it's not null. Can we reason about that and be sure p is not null? Well, look backwards. What's the loop condition? P not equal to null. So this loop body can't be executed if p is null. So we know we get to here, p is not null. And same here, p is not null. P is not changed. After here, after this, after line 25, p might be null, but the loop is then going around again. We know it for this arrow and this arrow, p is not null. So we can do that little reasoning step I talked about to assure ourselves we're not going to try and use a null pointer and get this sort of error. And you think, that's horrible, DCC doing that to me. Actually, DCC is really making life easy for you. What you'd get otherwise is, well, is the operating system giving you an error, probably. If you're on a tiny machine, you'd actually get weird behavior. But the operating system would just terminate your process with no information. DCC goes out of its way to tell you what's happening here and show you where it happened in your code and so on. Alright. So this prints a list. There we go. It will go down the list, and it doesn't matter how many things in the list. Yeah, lovely. Oh, we can simplify this a little bit, can't we? I might prefer to call this, something like list head. That would be nicer. So give me a pointer to the list head and I'll print out everything in the list. Now, if you're smart, you're thinking, right, okay, Andrews, we've just come up with code that prints out everything in a list. So if I want to do something for each list element, I replace that printf with the something. So if you've got a task you need to do for each list element, you put it here. So this is the equivalent of code for an array that says int I equals 0 while I less than array size, do something, I equals I plus 1. That executes over each array element in turn. This executes over each list element in turn. It's the most useful programming pattern, I'd say, for working with a linked list. Okay, that's quite nice. Right. What do I want to do now? Not that one, that's still to come. Yep. Oh, I've got a diagram of what we're doing. I should have used the diagram. So we start with a pointer here. Then we move the pointer to the next thing in the list. And eventually we get a null pointer, and then we stop. They're in diagrammatic form for you. Alright, the next task is we're going to use a linked list to track players in a game. This is an example that's going to span this lecture, and we're going to come back to it in Thursday's lecture as well. So we want to display the players in the game. We want to add players, remove players from the game. It sort of gives us a nice simple example for trying out some more ideas with linked lists. Yeah, so here's the idea. It's saying, let's just store the player name. Alright, let's work on that then. What's the point? So I'm going to copy all of this code over. Yeah, I've got this code. I've created this code now. I'm going to use it. Let's go. Alright. Let's copy it over and use it for a different task. Alright, so first thing, char name. So we'll store the player's name in an array. How long? I don't know. By the way, if you work with real data, particularly dealing with people, there's one thing that try to assume as little as possible about names. Names are one of the worst things to deal with in coding. There are all these things you'd like to assume about names to make your coding easier, and you can just assume none of them. There are people out there with names of all sorts, and so I assume names can be only 100 characters long, and that seems a lot to me, but no, there'll be people with names longer than that. But that's not our topic today. Alright, so we'll change our create node function to create a player, and it'll pass in their name. Oh, well, I'll call it new name for. We might as well put the max name length. Alright, let's let you autocomplete for me. And this becomes so we're going to make this a struct player, and a struct player, and we'll call this what, new next. All right. So we're going to create a few players. Alright, I think I've got a diagram here already with some player names, so let's try and be consistent with the player names. Yeah, alright. First player I've got to create is Mark. Mark, and then chicken. So Mark wrote this code. Chicken is his cat. Alright, and let's put a couple of the comp1 staff in there. We'll put Shrey, who looks after the forums. It'd be nice to Shrey. He's been doing a great job. And we'll put Anusha in there, who did assignment 1. So the tutor did assignment 1. And apologies if I'm not spelling your name correctly, Anusha. I think that's it. Alright, so I'll create a list of 4 players and I want to print it out. Alright. How do I... Alright. we'll change print list to print players. Let's see what other things we're doing. You're saying this seems a bit weird, Andrew. You're taking existing code and modifying things. If you're super clever, you can write code that we can use for multiple things, but we often end up taking code and modifying it because it's just a bit problematic making code that does many things. So this is not an uncommon task. Alright. Print players. I'll call that head. Or list head. Call it down there, that's okay. Print players. How do we change it to work? We say print players. Struct node star. Player star. And we will need to print out the player name. Okay. What type is the player name? See, it'd be nice to have the struct definition open in another window, wouldn't it? You'll get to doing this a lot. Just if you've got things open in multiple windows, try not to edit them twice. Never open an editor twice on the same file. If your editor is any good, it'll try and stop you doing that. But that always leads to sadness as you make changes and overwrite the changes you made in another window. So it's an array of char, a zero terminated array of char. So printf %s will print out a zero terminated array of char. Right, so I think I've modified my old print list function to handle our new struct that's got a name in it and a pointer to the next player. We're still using the same system, the same basic loop. The loop can stay unchanged while p not equal to null, p equals p next, because we've still got a next pointer. And you'll see struct after struct in all sorts of coding that has all sorts of things here for the information inside there, the payload. But it has this basic thing of we have a struct and a next field that takes us to the next element on the list. Yeah, we're almost there. I'm almost able to store a list of players. How are we doing? Oh, yeah, I think I can get this working in good time for us to take a break. Oh, what did I call this up here? We made it a bit more complicated, didn't it? Let's grab our definition from up here. We could make that prettier, I guess. How about that? There we go. Alright. I think I'm there. I think I'm there. I think that's good code. Alright, so I've gone through there, morphed my code that work with a list of integers to work with a list of player names. It's a nice demonstration of the fact that we can work with this, just this assuming that the node contains an integer, and explore algorithms. But when it comes time to write real code like this, we don't have to change much. The complicated stuff stays unchanged. Alright, so let's see if my code compiles. Let's see how we do here. Oh, so close. my god, how many errors can you get? Alright, this is an excellent thing. There's actually, I think there's probably only one or two things wrong with this program, but I'm seeing about 1 million errors, and it's a bit demoralizing. But what do? We take a deep breath, perhaps stand up and look out the window for a second, get a cup of coffee, get a cup of tea, whatever, then go to the first error. Just fix the first error. Alright, it says line 15, you've done something wrong. And this is a classic example of how you can get an error for 1 million things from one mistake. I forgot to change that struct node to a struct player. And because that's a variable declaration, I'm getting an error for everywhere that variable's declaration is used. It's saying, well, head, this, I don't know what that means, I don't know what this means, I don't know what this means, I don't know what that means. It's just giving a pile of errors. So we fix that, we recompile, and then we look at, and hopefully the number of errors is reduced. Well, there's less errors, there's still some errors. Still some errors. So let me clear this, take another breath, fix the first error. What's our first error here? Oh, and I've still got a struct node there somewhere. There. I guess if I was smart, I would have done a search in the file for struct node, or perhaps done an automatic replace of struct node with struct player. Yeah, they would have been smart things to do. Yeah, not that smart. Oh, but even though I'm not that smart, I'm down to one error. And this is a classic. This is an important. This is something you'll see over and over. So this line 36, that was good, where we were copying an int. You can just copy an int field with an assignment. You can't assign arrays. What's new name? It's an array. It's a char array. What's this field? Char array. Sadly, you can't copy arrays. We could put a loop there. We could put a loop there. But our friend here is, if we remember, we don't have to use a loop, because remember there's a function that does it for us. String copy. Yeah, you can't have vowels, can you? Alright, string copy. Important thing is to look at which parameters are where. So destination there, source there. So it's copy from and to. Important things to remember. So we're copying from and to. So our destination is there. Yeah. Oh, look, that's another way to remember that the ordering of the parameters for string copy and stru copy is it's like an assignment statement. So an assignment statement where you're assigning to is first, and next is where it's coming from. So it's parameters 1 and 2 of stru copy and string copy are just like that, from and to. And string copy says, oh look, it's an array, you better tell me how big the array is you're assigning to just to be safe. Here, that's probably not needed, but it's pretty good practice to use string copy anyway. String copy does actually return something, but typically you don't need it. Typically you just ignore what it returns, and that's okay. So I'm hoping that's fixed it. Yeah, there's some nice comments in the chat about how a smart person would change node to player all through this file. You can read those and oh, I guess if you're watching the recording you can't see the chat. Yeah, anyway, you can figure it out. It's not hard to figure out how to use gedit. A bit more smart than me. But even though I'm not that smart, oh, so close. No, I haven't saved my file either. I think this is right. I think. Oh, so close. It's saying string copy. What's string copy? Because we have to in hash include string.h. With a bit of luck, this will compile, work, and we can have a 5-minute break. Fingers crossed. All right. So we've created a list of 5 players and printed it out. A thing of beauty. Let me scroll down a bit. Yeah, all right. Unless Alvin tells me... Oh, Tom's back. He's as well. Unless Alvin or Tom has something they want that's urgent, we'll take a 5-minute break and then we'll take questions afterwards. I'll take silence for a yes. Actually, no. Let me look at. Oh, where are we at? No, I'll look at the chat. Yeah, we're way past break time. We'll take a break, then I'll scan the chat. We'll talk to Alvin, and we'll look at any questions. All right. So 5-minute break, and then we'll come back, and we're going to look at multi-file programs after the break. And talk to you then. Alright, hi everyone, we're back. Well, I left the video on during the break just so you could see the lovely code on the screen. Apologies, it was a bit confusing if I was talking to Alvin and Tom, which you couldn't hear. Not that it was particularly private, but alright. Oh, there's some good questions in the chat. I'll ask Alvin if there are any other ones. What about free? Someone's saying. Didn't you say, Andrew, there's got to be a malloc for every free? Yeah, we haven't got to that. But so this program's sort of incomplete. We're calling malloc there, but we're never calling free. So we have to free up a list. And that's sort of complicated. We won't get to that today. But so we haven't got to that yet. So there should be a free players call. Now, there was something Alvin was saying, this is the way you've done it, so it's sort of a bit too clever and a bit less obvious than you might have written it. He said, I might have used two variables. And yeah, Alvin's got a point there. So I've rewritten this code. This does exactly the same thing as it did before. You know, perhaps a more obvious way, and we like obvious, certainly. So I've added an extra variable called n, which can point at a struct player. And this will sort of make the steps of creating the list a bit more obvious. We start off with a list with nothing in it. So we say the head's null. So it points at nothing. So that's a list of 0 items. Oh, and if I do it like that, I really should change that as well to be head. That would make sense. Then I say create one item, put mark in its name field, and put the head of the list in its next field, and this will give us a list of one item, and we get that a pointer of that struct back in it. I've put that in, and then I can make that the new head of the list. I can repeat this again, saying, let's create a node containing chicken, a player chicken, and then the next for chicken will be the current first node in the list, first player in the list, mark. And you can repeat this over and over again. And we could do this 10 times, 50 times, a million times. We've just done it 4 times. Oh, and by the way, apologies to Anusha. That's how she spells her name. Yes. We do try at CSE to get be respectful, get people's names and pronouns right, and if we don't, we apologize and we try harder. Alright, get it right in future. So that code is exactly the same, but perhaps it's a bit more obvious. It's showing you these one lines where we put the head on the right side and create the player, and then assign the value we got straight back to head. Is a bit more compact. Let's undo all those changes and take. No, do I have to? No, maybe I don't have to undo all those. I'll leave that for now. So if a student wrote this code, I wouldn't be saying, by the way, it can be a bit demoralizing. It's a bit hard. You struggle with the code and you think, I've written this. It works. It's great. And then you see how your tutor would have written it, and it's 5 lines. It's half the size. That's normal. That's always the way as you learn to code. And I would never say to a student, you can make that code shorter. That's sort of written in an obvious way, and that's good. Alright. Actually, I should compile and make sure it's correct. I haven't left any errors in it. Alright, what do I want to show you now? There, we're going to change topics. Alright, changing topics. We're moving to Multifile C Programs. Let's look at... First thing I want to show you is something... I need a new window. I need to test a new construct. There's something called Typedef. I just want to show you briefly before we move into multi-file programs. Ooh, select a folder below. There we go. Let's do the usual boring stuff. Studio.h. What do I want to do? Alright, here's a nice little obvious program. Just print out a number. Let's run it. Print out 456. Great. Alright, that's not the point of all this. I wanted to show you a new keyword, which we'll see a little bit, not a huge amount, but a little bit at least as we work through this. C has a way of giving a name to a type. I can say in future I want to refer to this type by this name. Alright, and we're going to create a new type name. I'm going to call it Alvin. And you're going to say, yeah, that's silly. Yeah, I really want to make it obvious that this is what's happening here. So the name Alvin now means to see the type in. Let's make sure I've got that right. The orders in Typedef's a bit weird. If you come from other programming languages, you might be a little bit surprised. Yeah, that program does the same thing. So watch this. Anywhere I can previously use the type in, I can now put in the type Alvin. And there we go. So I can now create Alvin variables that hold an Alvin. You think, I can even do this. Have main return an Alvin. Are either of these good things? No, they're not. This is not something. Both of these are showing you how creating types can make your program much harder to read. So if you're used to reading C programs, even after 7 weeks, you're used to seeing int everywhere. So changing int to Alvin, it's making everyone's life harder, isn't it? Why would you do that? There are a few reasons you might want to give a name to a type. One is if you want to make your program easy to move across platforms where you might need to use a different type as you move to a different platform. What do I mean by that? You might write a program that has to work on hardware, embedded devices, things like washing machines or toasters, and types might change depending on what little CPU that you have there. So you might want to parameterize types for that reason. You might want to hide types in an interface, and it's to do with interfaces is why I wanted to show you Typedef. So that would be another reason for this. You can use Typedef to make your programs more readable. No, we won't be doing that much in this course, but that's another reason. We won't be using Typedef much, but I wanted to show you you're saying, oh, if I've got my own, how can I tell whether something's a type or a variable? If someone's creating, how can I tell if Alvin is a type or the name of a variable, the name of a type or a name of a variable? And that's important. So people often adopt conventions with that. So you can recognize types when you look at a program. You'll remember we've got that convention already. Hash defines. We always put hash defines in uppercase so we can recognize them, and that's a convention that's used almost universally. One you might see is append a little underscore t to types. That's the sort of thing people do, but that's not universal, far from universal, but that's one sort of trick. And by the way, you're saying one question you might have is, could I do this with a hash define? Yeah, it's more or less like a hash define, more or less. It's better than a hash define for sort of complicated reasons, but it's like doing a hash define, giving it something another name. All right, that's a Typedef. It's a name for a type. Yeah, so you can imagine a complicated program with thousands of lines where a type was used in many places. A type left lets us potentially change one line to change the whole program. All right. That was Typedef. What do I want to do? Oh, now I want to create multifile programs. In fact, we'll grab this. So I'm going to create a program across 2 files. So we're not going to use a Typedef. I want one. Oh, what have I done here? Oh no, this is what I want. In one file, I want to call. Sorry, Alvin, you're being dumped as a type. Function. I'll give it a parameter 2, and we'll print it out. I want to put in an. That's what we call this. You'd often call this. You often get called main.c, but I'm going to call it printanswer.c. Okay, save it. So that's what I've got in one file. In another file, I want to put the function answer, which takes an int parameter z and I don't know, returns z times 3 plus 5. All right. There we go. And we're going to call that one answer.c. All right. Now you're saying, this just seems like hard work, Andrew. Why would you split your functions across 2 files? Let me give you 2 reasons why I want to explore this. One is, in real code, you're saying, in this course, we're going to be working with pretty small programs. Even in assignment 2, it's probably not much of a problem for your assignment 2 to have it in one file. Its size is not a problem there. We'll split your assignment 2 across multiple files. Certainly for assignment 1, it wasn't much of a problem to have it in one file. Real code gets much bigger. So the Linux operating system is one big C program that I'm using right now. It's million-ish lines of source code. If it was a million lines of code in one file, just completely unmanageable. We can manage the complexity by splitting it between files. So the Linux operating system is split into roughly 60,000, I think it is, C files. So we can manage complexity by splitting in files. The other thing we can do is it also lets us help us share code. So if we've got common code that we want to use in 5 different programs, we can put the common code in separate files and use those separate files in these 5 programs. So it's sharing and managing complexity is our goal here. But first we're just going to see, can we make a program work with the function in one file and the main in the other? When we do this, the compile line looks like this. Suddenly we have 2 files on the compile line which contain all our functions. One crucial thing is there better be only one main function between these files. So up until now, every C file we've been created have a main function, but when we put our program across multiple files, there can only be one main. So I've done that. I've got a main function in print answer and a main function and just a regular function, not main, in answer. That should work. Actually, I'm going to change that to 13. Alright, and we'll put all of that in print answer. So this is my first attempt to combine two files. Alright. Now we've got a problem here. And the problem is we have to say what answer is. Oh, well, we've done that before, haven't we? So I can say answer, what is it? Double Z, wasn't it? Okay. Sorry, let me clear that notation. So I've done that. Alright, so I think I've got that right. But of course I haven't saved it. Oh, alright. I'll run my program. What will this do? Oh. That doesn't seem right. (13 times 3 plus 5). That should be 44, I think. How am I getting 8? How weird. Yeah, how strange. Alright, what I've, deliberately done here, I'm a horrible person, is made a mistake that will occur if you code like this. So I'm using function answer from over here. C, before you use a function, needs to be told what its arguments it takes, how many arguments, what types, what it returns. So I said, oh yeah, I'm going to using answer.c and this is its type. But that's actually wrong. I've got that wrong, haven't I? In this case, deliberately. The type of the argument to answer is actually int. And that's broken. What it does, I was actually surprised it printed 8. I was expecting to see a large negative number. But what it does, who knows what it does. It's not defined. This is illegal C. Because I've told C, this is what answer is, but I'm wrong. But C, there's an issue here. C, when it compiles a multifile program, compiles each file in isolation. That's actually handy if you're doing something like working on the Linux operating system with 50,000 files. It can be used to really speed up compilation because we don't have to work on all 50,000 files simultaneously. Someone's mentioning a tool called Make, which we're not going to get to in this course, which can really speed that up. But each file gets done in isolation. So C never checks that this matches what's over here. What do we do about that? What we do about that is create our own .h file. So if you're going to call a function from another file, you create a .h file. Let me show you how this works. I'm going to create a .h file and I'm going to call it answer.h. Oh, there's a subtle difference. I will show you the subtle difference when we get to the other file. And we'll go. So in the file with the function, we hash include answer.h. Over here, we hash include answer.h. Now, who can spot the difference? Hopefully you all can spot the difference. If it's our own .h file, we use double quotes to include it. If it's a built-in .h, we use angle brackets. So subtle syntax. Remember, it's key to success in computer is quickly spotting issues like that. All right. And you don't put the prototype for the function in either .c file. So we move it from there, we put it in the .h file. So let's create the .h file. And save as answer.h. Now if I try and compile like this, it will tell me inconsistent. Inconsistent is really what it's saying here. Because I've moved the prototype here, C, when it compiles this file, will check the prototype in here matches the real function. And that's what C is complaining about. And when I include it over here, I'll get the right prototype. So I can't no longer have this mismatch between files, because the .h file that's included in where the function's used, so this file which calls the function is including the .h file. This file which declares the function is including the .h file. And in the .h file is just the prototype of the function. Suddenly, which is wrong, we'll make it right, suddenly we can no longer have this inconsistency between files. Alright. Let's compile that, and hopefully that will print 44 like it's supposed to. So why was it printing 8? It can print anything there. Once you have an illegal C program, any sort of behavior is possible. At some stage there, it was probably getting the bits for part of how you represent a floating point number and a double, and turning them into an int, or vice versa. No, it's getting, yeah, it was who knows. But if you follow this rule, when you want to share a function, put a prototype in a .h file. Include the .h file where you define the function, include the .h file where you use the function. This problem just goes away. If you make a mistake, DCC or a C compiler will spot it. Alright, what else do we put in .h files? There are a few things we want to share between programs. You might put hash defines in a .h file because they need to be used between, they need to be anything you need to use in multiple C files, you put in the .h file. So if a hash define has to be in two .c files, you don't put it twice. That way leads bugs, that way leads pain, that way leads coding and fixing problems at 4 AM. You put the hash define in one place, a .h file, and include it in every file. So there might be max name len 1024, for example. Hash defines, functions, what else goes into .h files? If we have typedefs, we might want to share types between the files. So there was our silly redefinition or definition. Alvin is another name for the type int. You might put that in the .h file. Occasionally you need to include, there's a really important thing I forgot. A really important thing that goes in .h files. Structs. More important than typedef. Structs. So often we want to share structs between multiple C files. So we'd have a struct definition in a .h file. Yes, often. Occasionally .h files include other .h files. Why would you do that? Occasionally a .h file has a type you need from. So you might need to declare a struct, and to do that you might need a type which comes from another .h file. The order here is a bit weird. You'd probably put the .h file first and this last, but you're saying, Andrew, you're putting everything in .h files. No, I'm not. Let me show you the one thing you never do. You never put code in the .h file. So you'd never put what actually function does. Nothing that you really execute goes in a .h file. That's bad. Do not do that. So you'd never have, you know, this in here. You'd never put function f, what function f does. So we can say answer is what its prototype is, but we'd never put in the rest. You'd never say this bad, 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 this good. So we don't put the actual functions in .h files, we just put the stuff we have to share across files. Our .c files still contain the code, the real code. This is the stuff we need in multiple files. We want to put it in one place, the .h file, and include that in multiple files. So that's including things in a .h file. Alright, I want to peek at a more complicated example, I think. Let's check on the slides. There's probably a few things I've forgotten on the slides here, so let me look at the slides. There's Typedef's. Oh, by the way, yeah, let me re-emphasize two things from the slide. When I compile the program here, I don't mention the .h file. I mention all the .c files, don't need to mention the .h files. Plus, I could have one file, I could have two files, I could have 50 files, I could have 100 files. There can only be one main function. So if I got a million-line program broken into 70,000 files, one of those files, just one, has a main function. And that's where it all gets execution starts. So there's never really an absolute, any program that consists of 100 files can be turned into a program that consists of one file. If there are clashing names, it can be a little tricky, but it can be done. But we do it to allow us to share files between different programs. We do it to manage complexity, to make it possible to work with gigantic programs. That was Typedef. I think we've seen all of this information. That's the example we just worked through. Done slightly different, but it doesn't matter. Oh. Alright. I'm going to show you an example of an interface, a whole interface defined in a .h file. So if we want to use maybe pre-existing code, the .h can provide the definitions of how we interact with this pre-existing code. So let me show you some three files of pre-existing code, and let me open it. I think I've got them already here. So I've got a way of storing information about a person. Yeah, it's predefined. Alright, so when I store information about a person, this first gives me, well, these people have powers. Oh, I'm storing apparently superheroes. Okay, I'm storing information about superheroes. And a superhero, first there's some hash defines. My superheroes, the maximum name I can give a superhero is 50 when I work with this code to store information about a superhero. The maximum number of powers the superhero can apparently have is, it's 5. And each power is of length 50 as well. So that's a classic sort of thing. Yeah, that's a normal sort of thing. You're told, yeah, here's some functions that will store information about a superhero, but these are limits you've got to respect. There's an important thing here which we'll come back to, but there's a struct person. Sorry, oh no, that typedef is a struct person star. Alright, so that's giving the name person with a capital P. Oh, this is another convention. Yeah, people have a few conventions. Here the coder said, oh, how do I give people indication it's a type? I'll use a capital as the first letter, and that's also a common convention. So we said a struct person is that, and we're using that here. Ah, interesting. So that says I can create a person by passing a name, and I'll get back that. What's a capital P person? It's one of those. Yeah, this sort of, it creates a level of indirection that we continually have to think again. Every time you see a typedef name, then you have to go, oh, that means struct person star. A free person, to free up a person. Something to give a power to a person. Something to display a person. So we've got all of these things for storing information about a superhero. So this .h file defines the interface to use the code. Let's actually now try let's try using the code. So let me show you something that uses this interface. We're going to store information about Batman. We're going to give Batman 4 powers: display Batman, free Batman. So we're using all the things we just saw defined in that .h file. So we include the .h file there. This gives us this type, a person. We create the person, display them, give them some powers, display them again, free them. Let's try using that. Notice the .h file has defined us everything it needs to know. It's told us there's this function, there's this function, there's this function, there's this function. It's told you what the types are. You don't need to look at the internals. It's given you the interface, the outside view to this code. So we want batman.c, and the implementation of these functions is another file called person.c. And if I've got everything right, I can create this and try out these functions. And there we go. So that's using a .h file to work with code in person.c. We don't need to know what's in person.c. Why would we do this? It creates the interesting possibility in that we're no longer depending on what's person.c. So if we're a team of programmers, we can work over here on our file, they can work over here on their file, and as long as they keep the interface consistent, they can keep improving their code, we can improve our code. As long as the .h file doesn't change, we're good. This is our first view of an interface. It's a really important concept. But a .h file is defining this interface for us. We never find out what a struct person is. Our code doesn't know what a struct person is. That's another common way of doing this sort of thing. We're not told what the internals of the representation are. You want to create a person, call this function. When you're done with it, call this function. You want to give them a power, call this function. You want to display them, call this function. You're never told what actually is in there, how it's done. That means the coders working on person.c can change the internals without worrying about us depending on them. They've never told us what the internals are. So then they can't break our code because our code can't depend on the internals. It can only use this interface. This is crucial to, again, managing complexity. We're limiting the connection between these two pieces of code to this file. So person.h is setting out, you can call this function, you can call that function, these are their types, but that's all. So this is the connection between the outside world, and person.c, which manages our complexity. This is how we can actually create 50,000 files and 1 million lines of code in a program and have it all work, have it work really well. So I'm right now, I do something like that. It's executing into 1 million lines of C code, and it's all working reliably. Doing incredibly complicated things in the operating system because we manage complexity like this, limit the connection between files so we can work on particular files in isolation. Yes, Eric's asking in the chat is you don't say what create person does in the .h file. Yeah, you never put the actual body of the function. You'll never have a curly bracket here and code in a .h file. You just say what are the types. It takes three arguments of these types, returns this. You just give the function, I call it prototype. And we just say it's a struct person. We don't actually, C is nice like that. You don't have to say what's in a struct person. That's hidden off, and that's hidden off what actually is in person.c. We'll peek briefly at person.c, and then I might try and see if I can get a little bit more done about lists. We'll just peek briefly at person.c, and in person.c is the actual struct, and there's code there to create a person, free a person, add powers, display person, and you can read that as your leisure. That's all on the course website, but that's not the important thing. The important thing is person.h that gives us this interface, and then batman.c which uses this interface. So that's connecting via this .h file to these functions. It's a lovely example there. All right. Sorry, but I want to talk a bit more. I'm rushing, I know. I'd like to finish here, but I want to go back just for a few minutes, in the few minutes we have left, to linked lists and talk a bit more, because there's I think a bit more I can usefully cover for this week's lab. I wanted to cover that multi-file things. You do use multiple files in this week's lab in a fairly simple way, but also when Zoe and Tom take on explaining the assignment, assignment 2 uses multiple files and very much an interface like we've just seen. Alright, that's creating a player, printing out the players, inserting into a list. Yet linked lists give the possibility of putting a node into the list. Let's go right back to my first slide. Sorry to give you. So we've created new nodes and put them here. It would also be possible to put a new node here and change that field to point to it and make this one null. But you could also put a node in anywhere. So let's look at the possibility of adding a node in other places. Oh, sorry, keep going. Keep going. So we can find the spot in the list we want to do. We can take the next of the first first node and point it at our new node, and take the next to the new node and point it at the second node. So if you imagine as a chain of links, we open up the chain, link our new link in, and connect it back into the chain. How does that work? If we have this situation and we're trying to put something here, what do? So how do we get a new list with a node sitting between the first node and the second node? First we create the new node. There it is. It's got nothing in here, but it's got 3 in there. How do we what do we want to do? Well, its next field we want to point to there, and this next field we want to point to there. Well, it doesn't seem that hard. And trust me, it is. Getting it right is seriously challenging coding. So, yep, copy this field to there, and that's what we want. Well, that's not so hard. Then change this field to point to there, and we're done. Oh. Yeah. All right. Let's start in on this. I'll go back to just my lists of integers. Actually, no. We'll do it with Battle Royale. That was simple. Yeah, that's okay. So we want an insert after. I'm just trying to keep it consistent with what I got on the website. Oh no, alright, we'll just code it up. Alright. So that's the function I'm looking to create here. It takes a pointer to a node and inserts this new node after it. So how do we do it? Oh, not new node, I call it new player. Yeah, it's almost simple. This is not the full story. So the next field of the new player has to be a copy of the next field of the node we're inserting after. And the node we're inserting after, its next field has to become the new player. And that's what we've got to do. There's a case I'm missing. Yes, there's a case I'm missing. But that works most of the time. If I go back, that's the two steps we've got to do. That's one assignment, make this next field point there, and that's the next assignment, make this happen. So I've coded that up. Those are the two operations to insert a player after some particular point. So let's try it out. Let's create a player. We'll create a player. Oh, Zoe did the assignment, so I'll create a player Zoe. Doesn't matter what we put in the next field because that's going to get changed. So that creates a player Zoe sitting by itself. And then we're going to do insert after. Where will we insert it? We'll insert it after the second element of the list. And then we'll print the players out. There we go. All right. Have I got all of that right? Will that work? So close. Oh. All right. Yeah, we could do it. That's true. We could have made Zoe a new variable. There we go. That will work. And we haven't declared the function. Non-void function. Oh, yeah, what's it return? Oh, well. What does it return? Yeah, interesting. Yeah, we'll come back to that. This function is half complete. We're not using the value currently. So I'm going to return the new player. Alright. Better still, we'll just make you void for now. Actually, we'll just and there we've inserted Zoe successfully into the list. Alright, so that's our taste of manipulating lists by pushing a node in the middle of the list. There's a problem with this function. There's a case it doesn't handle. That's the general case. That's the big one. But there's a case we haven't handled. It's actually in the lecture slides if you want to cheat and go ahead. But that's inserting a player into the list. But we're out of time for today. I'm going to ask Alvin if there's any crucial questions in the chat, but we're already 3 minutes past the hour, so
Nothing from me.
nothing from Alvin, so apologies for running a little late. But yeah, we've done that crucial bit, and if you want to, we're going to cover this in careful detail in the next lecture and expand on it, but there's some slides there if you want to go ahead on that. Alright, good luck with the lab exercises this week. There's lots to cover, so much to cover there. Live stream for the assignment with Zoe and Tom coming tomorrow, and we're back to linked lists on Thursday. Thank you, Alvin, for listening in. Thank you, Luca, for managing the chat. Apologies we haven't had time to get back to your questions, but we'll have more time on Thursday to get going through any questions you've got in the chat. So I'll talk to you all then.